Hi everybody, welcome back to my channel on Feynman integration. Today we're going to be discussing a topic that's closely related to Feynman integration, although we won't actually be solving an integral using the process. Today what we'll be discussing is something called the Laplace transform. It's used very often in engineering type, in physics classes like electrical engineering, or physics, or it might even be introduced in some classes on differential equations. But anyway, oh, and I also want to note that normally the Laplace transform involves functions of t and s, but in keeping with the kind of tradition of this channel, I'm going to be working with functions of x and t. Like I said, normally it would be transforming a function of t into a function of s, but since I have always been transforming functions of x into functions of t, that's what we're going to keep doing. So anyway, the Laplace transform of any function of x is defined this way. It is the integral from 0 to infinity of that same function of x times e to the negative xt dx. And that is going to be, as you can see, a function of t. So Laplace transform takes a function of x and transforms it into a function of t like that. One quick note, I didn't write it on the board here, but obviously the Laplace transform of 0 is going to be 0. You can see that pretty clearly up there. And then also the Laplace transform of any constant is going to be equal to the integral from 0 to infinity of that constant, because that constant is our function of x in this case. So it would be that constant, in this case a, times the integral from 0 to infinity of e to the negative xt dx, which you guys can all evaluate that. That's going to be a over t. So if you see the Laplace transform of any constant, it will be equal to a over t. Example number 2 is the Laplace transform of a power of x. And in this case, that n is, that it does need to be an integer. I'm not sure if it needs to be a positive integer or not. Maybe I'll do an addendum to this video at some point. But anyway, the Laplace transform of any of x to any power is going to be n factorial over t to the n plus 1. And this right here, if you'd like an explanation of that, I already did that in one of my earlier videos, and this was one of the results we got when I was trying to when I was demonstrating the integral representation of the factorial function, and we did arrive at this. So anyway, that's where that comes from. I didn't show any of the work involved in it. You can watch that video if you want to see it. Example number 3, the Laplace transform of e to some constant times x, and e to the ax is equal to, let's see, our function of x would be e to the ax times e to the negative xt. Using the properties of exponents, factoring out the negative x, you'll get that Laplace transform of e to the ax is equal to the integral from 0 to infinity of e to the negative x times quantity a minus t dx. And you can all evaluate that yourselves. That will be 1 over a minus t. Those are a few examples. There are tables and tables and tables of these things. It would be, my life's work to do a video on every single one of them. But you can do them all yourself. The only thing you need to know really about the Laplace transform is this. And you can get all the other stuff, if you're fairly competent at integration. Some other useful ones are like the Laplace transform of the sine function, the cosine function. One of the big ones, though, that I think I might utilize in later videos is Laplace transforms of derivatives. So let's just start with this. We're going to take the Laplace transform of the derivative of some function of x. So the Laplace transform of f prime of x. So all we do is we just plug it into our equation there. So the Laplace transform of f prime of x is equal to the integral from 0 to infinity of f prime of x times e to the negative xt dx. That requires that you could all do that. I mean, it's not that difficult. It's a little messy, but all you need to do is, you know, do integration by parts. And I use, you can see right here, I use the DI method, which was made popular it existed before black pen, red pen, obviously, but it was really made popular by him, and I like it, so I use it. Anyway, we need to choose what part of this we want to differentiate and what part we want to integrate. So, I mean, the choice is obvious. You want to integrate the derivative, so you get back the original function. And so we will differentiate what's left, which is e to the negative xt. So the derivative of e to the negative xt is negative t e to the negative xt, and the integral of f prime of x is simply f of x. Continuing on, we get that the Laplace transform of f prime of x is equal to, normally what black pen, red pen likes to do is he likes to make a little note that this is positive and this is negative. What that means is you'll be taking positive e to the negative xt times f of x and evaluating it over your bounds. That's right here. And then you will be subtracting the integral from 0 to infinity of negative t e to the negative xt f of x. And that's right here. So, again, the Laplace transform of f prime of x is equal to e to the negative xt times f of x evaluated between the bounds, plus t times the integral from 0 to infinity of f of x times e to the negative xt dx. Finally, when we plug in the bounds here and evaluate that, or, well, I'll show you anyway. So the Laplace transform of f prime of x is equal to, so this part right here comes from this. You'll notice that this is exactly the definition of the Laplace transform. So this is literally our Laplace transform of f of x. So this part right here is t times the Laplace transform of f of x right here. And then if you plug in these bounds, you'll notice that if you plug in infinity, it will evaluate to 0, because e to the negative infinity is 0. And if you plug in 0, you will simply get 1 times f of 0, and that is where that f of 0 came in, right there. So the Laplace transform of a derivative of a function is equal to t times the Laplace transform of that original function minus the original function evaluated at 0. I'm not going to show the work for the second derivative. It's the exact same. It's there's more work to it, but eventually you keep doing that and a pattern emerges. So the Laplace transform of the second derivative of a function of x is equal to t squared times the Laplace transform of that original function of x minus t times the original function evaluated at 0 minus the derivative of that function evaluated at 0. So, and you can keep doing that. You can go all the way up to the nth derivative of x, which is what we did right here. So, this is the pattern. This is the pattern that emerges if you keep taking higher and higher derivatives of your function of x, and then taking its Laplace transform. You will get this. And I'm not gonna say all of that because it's a mouthful. But anyway, that's what it is. We're not actually going to be solving a problem today. I just intended this video to be an introduction to the idea of the Laplace transform, and the main thing we will be utilizing the Laplace transform for is taking Laplace transforms of derivatives of functions in later videos. So anyway, that's it. Play around with it. Try to evaluate some of the other Laplace transforms yourself. And then maybe, definitely in a later video, we'll be discussing inverse Laplace transforms and how to use them. Should be no mystery what the inverse Laplace transform is it's basically just going backwards. So anyway, in a later video, we'll be discussing that, and I hope you enjoyed that.